Pluto is a far-off and baffling diminutive planet that was once an individual member of our planetary family. However, late frightening declarations by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They recommend that this frosty world is on a potential impact course with Neptune. Yet how might this occur, and what would be the outcomes of such a monstrous event? Are we seeing an interesting cosmic peculiarity, or is there something else to this approaching grandiose impact? Join us as we investigate the potential outcomes of a Pluto-Neptune influence. Pluto, a previous planet that was downgraded to a dwarf planet, partially because of its unconventional orbit, remains a subject of interest and study in the cosmic community. According to recent forecasts by leading researchers, Pluto's trajectory is hazardously near Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential dangerous impact between these two planets that could pose a colossal danger to Earth. How is such an event even conceivable? Pluto's excursion around the Sun is unlike any other planet in our nearby planetary system. It takes a stunning 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full transformation. Yet the interest doesn't stop there. Pluto's path is marked by its profoundly curved shape, veering off significantly from the nearly round orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, calculated at 17 degrees to the ecliptic plane. The path Pluto follows is much more extreme compared to the other planets. This inclination and eccentric nature add layers of complexity to its orbital pattern. Quite possibly one of the most interesting aspects of Pluto's orbit is its intersection with Neptune's. For around 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we would expect from their positions in the solar system. This prompts the natural inquiry: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to grasp its unique trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of space mechanics. The three-body problem in space is about figuring out how three objects like Pluto, Neptune, and the Sun move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. For Pluto, this issue illustrates how its path, Neptune's orbit, and the Sun's gravity all work together in a complex manner. The terms alpha libration and scope libration, along with the VZK oscillation, are part of this puzzle, as indicated by astrophysicists. What's keeping all planets in their orbits is a phenomenon called alpha libration. In relation to Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is situated about 90 degrees away from Neptune. This spatial separation is crucial in keeping their paths from impacting. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned significantly above their orbital plane, providing an extra layer of security from potential impacts. Another significant aspect of this situation is the VZK oscillation, named after three researchers, Bond, Zipper, and Kai, who studied how objects move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This pulling influences how they move. In Pluto's case, VZK helps us understand why its path around the Sun is so unusual. Despite the fact that Pluto's orbit appears to be all over the place, this oscillation helps keep it moving smoothly from now onward indefinitely. The VZK oscillation shows that even if things in space seem wild and irregular, some patterns and rules keep everything together. All of these factors help maintain Pluto's orbit, ensuring it doesn't collide with Neptune or lose its course. This three-body problem assists in understanding how these paths change based on the way these space objects pull on one another. Focusing on this helps us learn more about Pluto, our nearby planetary system, and distant worlds and their stars. Mathematical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is, in fact, turbulent, with minor deviations in initial conditions leading to significant differences over thousands of years. Nevertheless, these interesting properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos in check. Recent computer simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's path around the Sun. Neptune has a special relationship with Pluto, where for every 2 rounds Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only planet at play. Jupiter's gravity also plays a huge role in safeguarding Pluto's orbit, and Saturn contributes significantly as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for a very long time, even billions of years. So it seems like Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move securely in space without running into trouble. These phenomena are fundamental in the context of the universe for maintaining the order and stability of celestial movements. Without these components, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially crash into others or be catapulted from their stable orbits, leading to a cascading effect on other celestial bodies. For Pluto, particularly with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This provides us with a clearer image of the nearby planetary system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of harmony through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of ongoing observation and investigation of these phenomena to better grasp our place in the universe. Exploring the depths of space often leads us to confront the erratic nature of celestial bodies, and Pluto's orbit is a perfect representation of this eccentricity. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is distinctively outlined in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly shift its long-term trajectory. In the vast field of our solar system, Pluto occupies a unique place that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant revelations about its composition and behavior. One of the most intriguing features of Pluto is its surface, which is an intricate embroidery of ice, rock, and various mixtures. The New Horizons mission, which flew by Pluto in July 2015, provided exceptional data about this distant world. The outer layer of Pluto is characterized by vast fields, towering mountains, and deep valleys. One of the most striking features is the Sputnik planum, a massive heart-shaped plain primarily made of nitrogen ice. This region showcases a diverse array of landforms, including huge ice shelves and what appear to be flowing glaciers. The presence of these features indicates that Pluto might still be geologically active despite its significant distance from the Sun and low temperatures. Another interesting aspect of Pluto is its atmosphere, predominantly composed of nitrogen with traces of methane and carbon monoxide. Pluto's atmosphere is tenuous, yet it exhibits fascinating seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior is a reflection of the complex relationship between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The relationship between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies orbit a point in space that lies between them, rather than Pluto simply rotating around Charon. This unique relationship contributes to the intricate gravitational dynamics in the region, affecting the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to numerous other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, providing researchers with a glimpse into its formation. Pluto's orbital attributes could offer insights into the migration patterns of these distant objects, suggesting that interactions with larger planets might have played a pivotal role in shaping their current orbits. One of the key implications of understanding Pluto's orbital dynamics is the potential impact on our comprehension of the solar system's evolution. The gravitational effects from neighboring giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can result in shifts in orbits, potentially leading to impacts or ejections from the nearby solar system. As scientists continue to explore the details of these interactions, they may uncover broader patterns that govern the behavior of celestial bodies throughout the cosmos. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to rename Pluto as a dwarf planet in 2006 was contentious, igniting debates about what constitutes a planet. The International Astronomical Union's definition focused on criteria such as orbital dominance and size, leaving many to ponder the implications of such classifications. This ongoing discussion reflects our evolving understanding of the universe and underscores the need for a flexible approach to categorizing celestial bodies. Furthermore, the potential for future exploration of Pluto and the Kuiper Belt remains an exciting frontier. With advances in technology and mission planning, scientists envision sending additional spacecraft to study not only Pluto but also other distant objects that share its orbital characteristics. Such missions could provide valuable information about the primordial materials that formed our solar system, potentially offering clues to the origins of life on Earth. The role of exoplanets, or planets beyond our solar system, is another captivating area of study that intersects with our understanding of Pluto. As astronomers discover an increasing number of exoplanets, especially in the habitable zones of their stars, the patterns learned from studying our own solar system can inform hypotheses about planetary formation and habitability. The conditions that enable stable orbits, atmospheric retention, and geological activity could shed light on the potential for life elsewhere in the universe. Finally, public interest in Pluto has endured, fueled by its enigmatic status and the stunning images sent back by the New Horizons mission. The dwarf planet has captured the imagination of people worldwide, inspiring a renewed appreciation for the vastness of space and our place within it. As we continue to unravel the mysteries of Pluto and the celestial bodies that share its region of space, we are reminded of the vast wonders that the universe has to offer. Do Pluto's special qualities extend beyond its physical properties and orbit? It too serves as a crucial case study for understanding planetary formation and the dynamics of celestial bodies. The formation of Pluto is believed to have occurred in the early solar system alongside other Kuiper Belt objects. Studying its composition can shed light on the conditions prevalent during the solar system's infancy, potentially illuminating theories about the formation of terrestrial planets, including Earth. Recent research suggests that Pluto may have a subsurface ocean, a discovery that could change our understanding of its geology and potential for hosting life. Data from the New Horizons mission indicated that some areas of Pluto's surface, such as the icy mountains, might be composed of water ice, which behaves uniquely compared to regular rock under low temperatures. This revelation invites further investigation into the possibility of liquid water existing beneath its icy exterior, raising intriguing questions about the potential for life even in such extreme conditions. Moreover, Pluto's relationship with its environment can provide insights into atmospheric science. The seasonal changes in its thin atmosphere offer a natural laboratory for studying atmospheric dynamics on a planetary scale. Scientists are particularly interested in how the interaction between solar radiation and the surface can lead to complex weather patterns, much like those observed on larger planets. The significance of ongoing surveillance of Pluto and other celestial bodies cannot be overstated. As more missions are planned, such as those targeting the far reaches of the Kuiper Belt, we can expect a wealth of new data that challenges existing theories and expands our understanding of planetary science. Every discovery adds another piece to the puzzle of our solar system's history and the processes that govern its evolution. Through these studies, Pluto remains a symbol of the relentless quest for knowledge about our universe, inviting both scientists and enthusiasts alike to ponder the mysteries that lie beyond our home planet.